Hi everyone. Today I'm talking to Jelmer Renema about a thermodynamic simulation that he's conducted on a quantum integrated photonic processor. We're going to be pretty focused on the interaction between quantum mechanics and thermodynamics in this video, so if you're interested in that, I think this will be a very good video for you. Let's jump into it. Jelmer, thanks a lot for joining the session.
Thank you.
Before we get started, would you mind briefly introducing yourself, just professionally what you're doing now, and maybe also how this paper came about that we're going to be discussing today?
Sure. So my name is Jelmer Renema. I'm an assistant professor at the University of Twente in the Netherlands, and I'm also the chief scientist at QuiX Quantum, a quantum computing hardware startup. And this paper came about, actually this paper has quite a long prehistory, so this dates back to an idea that Nathan Walk, who was one of the co-authors, and I had in 2016, 2017, where we thought, what if you take a system of photons, so particles of light, and you shuffle them around? If you shuffle them around enough, can you see the emergence of thermodynamics? So can you see the emergence of disorder? And the answer turned out to be yes, and that was the beginning of a long series of first theoretical and then experimental explorations, which eventually culminated in this paper, which was published earlier this year.
Mm-hmm. If we're talking about detecting the emergence of thermodynamics in general, are there any other approaches that are currently being taken for that particular purpose? Or was this sort of a novel idea to try and address some form of problem that we haven't had a way of addressing in the past?
It's a bit of both. So it turns out that there's been this... So what is at the heart of this paper is that there's been this really interesting apparent contradiction that we've known about for a long time between thermodynamics on the one hand and quantum mechanics on the other hand. So it turns out that thermodynamics, which is sort of the theory that governs the kind of large-scale systems that we encounter in our everyday lives, is an information lossy theory, right? So that means the example that I always give is, paintings fading, right? If I take two paintings and I put them out in the sun, or two photographs and they fade completely, then the information of which painting is which is lost, right? Mm-hmm. And that means a bunch of things. It means that within thermodynamics, you have a notion of time moving forward being very different than time moving backward, right? Because there is a direction of time where information is lost. So if you take a video of a thermodynamic process and you play it backwards, you can tell which direction, right? You can tell which is which. You can tell when the video is being played forward and when the video is being played backward. Mm-hmm. So information loss implies an arrow of time. And information loss also implies a notion of entropy, right? Because entropy is a measure of disorder, if you want. And so when you have this information loss, this is associated with the creation of entropy. So that's thermodynamics on the one hand. And then, by contrast, quantum mechanics is very much an information conserving theory. And so in quantum mechanics, setting aside the measurement problem for the moment, but like regular evolution of quantum mechanical systems is completely time reversible, right? So unlike thermodynamic systems where you can tell which way represents time moving forward, in quantum mechanics, you can't, right? So playing the video forwards looks exactly the same as playing the video backwards. Mm-hmm. And that also means that there isn't really a meaningful arrow of time in that sense. And it also means that disorder or entropy, if you want, is, at least for closed systems, is a conserved quantity, right? So we have this really interesting paradox on the one hand between thermodynamic systems, which are asymmetric in time and information lossy, and quantum mechanical systems, which are information preserving and time symmetrical, if you want. Mm-hmm. And we've known about that since the beginning of the 20th century. Like, pretty much as soon as quantum theory was set up, people noticed this. And there's been various steps made to try and resolve this problem. And I think the main, I would say, like, the big step that you need to know about, which is also cited in this paper, is the observation that you can resolve this paradox by making a distinction between systems as a whole and subsystems, right? Mm-hmm. So it turns out, and you can make this mathematically rigorous, that the time evolution of a system as a whole is governed by quantum mechanics. And if that's true, then it turns out that the time evolution of the subsystems is governed by thermodynamics. And mm-hmm. So where does the information go? The answer is the information goes to the quantum mechanical correlations between the different subsystems. So if you imagine that you have some larger system that is made up of a bunch of smaller subsystems, each of these smaller subsystems start out in some definite state, time runs forward, and the information kind of migrates from these subsystems to the space between the subsystems, if you want. And so if you look at a single subsystem, it appears to be disordered, but it isn't, right? At least the subsystem itself is disordered, but that disorder comes because you haven't looked at the correlations between that subsystem and all the other systems. And those correlations, that's where the order is hiding. Mm-hmm. And so what we set out to do is we set out to show that in a photonic system. So a system where your particles are particles of light. And why did we do that with photonics? Because it turns out that photonics is a very good, is a very long-lived, very stable carrier of information. And that means that you can do certain things in photonics that are harder to do in other systems. So people have probed this problem also experimentally in various other experimental systems, particularly cold atoms. So large systems of individual atoms moving around in atomic lattices, for example, in optical lattices, sorry, people have done these kinds of experiments there. The big advantage of photonics is the high coherence times, right? So it's very easy. Photons hardly interact with the environment. And so it's very easy to keep your photons stable. And in particular, what that allows you to do is it allows you to explicitly show this time reversal, right? So what I was saying was that quantum mechanics is an information preserving theory, and it turns out that you can prove that by bringing your system back to the original state, right? So what we do in this paper...
Sorry, one second. Would it be fine if I interrupt here with a couple of questions on the earlier material? So I think we can look at the paper and also look at the setup for how you do the measurement with the with the photonic setup in just a while. Before we go there, I would just like to probe you on a couple of things with respect to the things you mentioned before. The first one of those would be on the time reversibility aspect, just to get a bit more rigorous on what we mean when we say that. So we're saying quantum mechanics is time reversible and thermodynamics is not. And
Yes.
the example you use to illustrate what the difference is let's say you have a video of a process evolving according to one or the other. With thermodynamics, you would be able to tell whether you reverse the video. Is that a, let's say, semi-formal definition of what time reversibility is, or are we lacking some other fundamental concept that also makes up that, that also makes up time reversibility? Is this the only consideration? Like, let's say you have these two systems and both of them, you can tell for either one what the arrow of time is, let's say, if you watch the video of it. Would both of those qualify as time reversible, so that this loose definition that we gave now is sort of everything you need to conceptually think about when we talk about that concept?
Well, you can make it more rigorous by essentially looking at the equations and seeing what happens if you just, substitute time for negative time, right? And so the way in which quantum mechanics is time symmetric is that if you run time forward under a certain interaction, there is always another interaction that you can find that would give you the same dynamics if you ran time backwards, which is the same thing as saying that if you run an interaction, you can always reverse it under some other interaction. Right, and that's not true for thermodynamics, right? If I take a gas, right, and I take a gas and I put it in some volume, and I open a little hatch so that the gas can move into a second volume, right? It can spread, then it isn't spontaneously all going to move, right? All the molecules in the gas aren't spontaneously going to move either to the first volume or to the second volume. And there isn't really anything I can do that doesn't involve creating heat, right? Which is itself a time irreversible thing. So there isn't anything that I can do to restore the original situation. Right, and that's the essential difference.
Okay, thank you for the explanation. The second question I would have is, when we're talking about reconciling quantum mechanics with thermodynamics, or potentially doing that, this investigation could potentially be one step along that direction, as I understood it. One thing that surprised me with reading this, though, is the quantum aspect of this is actually the larger scale, right? So if we consider the system, the entire system is now evolving under a unitary evolution, and we're seeing local thermalization in the subregions of this, which is, intuitively speaking, from my perspective at least, the opposite of what I would expect. So we have quantum mechanics, which is a theory that explains, let's say, the time evolution of systems on the very small scale, that in some way then transitions into these laws of thermodynamics that we know from the macro scale. How come you have this inverse, the inverse relation here, let's say, between the two?
That's a very interesting way of looking at it. And to be totally honest, I had never thought about that. I think that it's natural to, right, in some sense, I would almost say this is precisely what, this is precisely why it took some decades to find the resolution of this paradox, right? Because you have to, you have to put quantum mechanics on the larger system, which is indeed kind of, if you look at it sort of naively, is kind of counterintuitive. But if you actually think about it for a bit, having a right, you can also, like, maybe one way that makes this more natural is to realize that there is nothing in quantum mechanics that itself refers to a scale, right? So people like to say, quantum mechanics is the is the theory of small systems, but I would say quantum mechanics is a theory that most easily manifests itself at small systems. But there's no reason to think that quantum mechanics isn't true for large systems as well, right? It just happens that it doesn't manifest itself for larger systems. And in fact, these theoretical results that show this relationship between entanglement, thermalization, and quantum mechanics precisely are part of the explanation of why that is the case, right? And so it becomes a bit easier to see when you say, well, hang on, the universe is a closed system, presumably, right? Mm-hmm. Like I would say almost definitionally, if you say, well, the universe is all that there is, right? In order for it not to be a closed system, there needs to be something that it can interact with. And so, by definition, that's not possible. And so as you go larger and larger, you eventually have to find a closed system again. And for that closed system, quantum mechanics has to hold, right? So if you come in from, right, if you sort of reason from this top-down direction, then it actually makes a lot of sense that quantum mechanics is the theory that describes the large-scale systems, because those are the closed systems.
Mm-hmm. Yeah, that's a very interesting take on it. So to also make it more concrete, we have the image here from the paper that sort of illustrates visually what we've been talking about. So we have on the large scale here global purity of this system. Would you mind also just defining that term, what that actually means, and then maybe describing what the local equilibration here illustrates?
Okay, so purity is a measure in quantum mechanics that you can basically think of as directly related to entropy, right? So it means the degree to which classical uncertainty has crept into your quantum state. And if there is low purity, then there is no classical uncertainty in your quantum state. Sorry, if there's high purity, then there's no classical uncertainty in your quantum state, and vice versa, right? So low purity means a high degree of classical uncertainty, or if you want to say it differently, a high degree of entropy. Mm-hmm. And then local equilibration essentially means that you are seeing this effect that I was talking about earlier, right? So that the variables which you can look at locally, they appear as if the system has undergone evolution, right? They take the values that the system would have taken if it would have followed the laws of thermodynamics, right? So locally, it appears as if the laws of thermodynamics are applying.
And that's irrespective of where you look locally in the system as well, as I understood it. Like you could also imagine that if you have an entanglement between two parts of the system, that one would, let's say, increase in entropy, and the other one would, on the contrary to that, decrease in entropy. But that's not what happens, right? What happens is both of them have thermal equilibration that's being displayed, and then the information, as you said in the beginning, gets then trapped, let's say, in the entanglement of these two.
Yeah, and I think what you're describing, I mean, there's two ways to see that what you're describing is very unlikely. The first one is to consider that to decrease entropy locally, you would have to do work, right? So, and then the question is, again, if you take this view of the system as the universe, right, that work has to come externally. So where would that work come from? Right, because there needs to be something doing work on the system. So that's one aspect of it. And the other aspect of it is, and this is actually where the theory gets pretty interesting, and where, to the best of my knowledge, there's also still open problems being worked on, is that this mechanism that I just described, there's kind of two ways that you can think of it. So you can think of it by saying, well, I'm going to write down some generic Hamiltonian, right? So I'm going to write down some generic time evolution, and then I'm going to show that time evolution does all of the things that I just said that it does, right? So, or the other thing that I can do is, instead of writing down a time evolution, I can write down a quantum state, right? So I just say, well, never mind how I got there. I'm just going to say that in general, time evolution under any reasonable Hamiltonian produces a large amount of entanglement. And so I'm going to look at highly entangled quantum states, and I'm going to show that substates of those highly entangled quantum states appear thermal. And that approach, like that you can prove rigorously, right? So you can make statements along the lines of, well, I pick a random quantum state according to some reasonable procedure, and I look at some subset of it, and then I start seeing thermodynamic effects. But for the approach where you look at Hamiltonians, which is sort of the more satisfying approach, because it gets rid of this slightly messy procedure of saying, well, we're just going to sort of randomly generate a quantum state. For that approach, you need to prove it. You need to prove that this is true Hamiltonian by Hamiltonian, right? Or for each class of Hamiltonians that you might be interested in. And in fact, one of the interesting kind of side topics which arose from this paper is that it turns out that some of the Hamiltonians that we probed that hadn't actually been proven for yet. And so I think that's like a really neat illustration of how you can sometimes have a fruitful, you can have a fruitful dialogue between experimental and theoretical physics that isn't just about the experimentalists doing what the theorists say they should be doing, right? So actually very often the dialogue between experimental and theoretical physics is about the experimentalists saying, hey, hang on, this thing is relevant because we see it in nature, or sometimes a bit more opportunistically, this is relevant because it's the thing that we can make, so you had better care about it. Right? And then the theorists actually going back and saying, okay, then we had better go and study that thing.
Right. Yes. When it comes to the actual Hamiltonians that you could apply to a system like this, would you more or less always observe this kind of behavior? Or is this an edge case only related to specific Hamiltonians? The emergence of these entanglements between different parts of the system that result in the local equilibration for these, is that something you would generally observe, more or less irrespective of the Hamiltonian you apply, or is it only limited to a very selective set of Hamiltonians?
It's in fact the other way around. So there exist Hamiltonians for which you don't observe this, but you have to, for example, if you say that your Hamiltonian is just zero, right? So the particles don't interact, they don't do anything, then they start, and because they start out not in a thermal state, they end up not in a thermal state, right? And so it turns out that in order to not see this effect, you have to very carefully fine-tune the interaction, right? Okay. So there's some set of Hamiltonians of measure zero where this effect doesn't manifest. But for a generic Hamiltonian, it does.
Perfect. So now, finally, I'll let you go back to the place we were, which is on the actual photon interaction with this, and we can maybe have a look at the setup that was used for the experiment as well. So if you would like to just resume the discussion where we were, like using photons now to measure these properties that we've been discussing and how that relates to the setup.
Sure. So the idea that we had was to use specifically photons to study these effects. And I want to say a little bit, before we go into the experimental setup, I want to say a little bit about this notion of reversibility, right? So where photons are strong, particularly, is that you can run the interaction forward, not have any decoherence, and then run the interaction backward, right? And so one of the things that this paper does, which actually the people in Cold Atoms, they have also succeeded in doing this. But it is still, I think if you want to go to larger systems, there are still strong advantages that photons have. Right, so what you see here, let me to then go to the system, is you see on the left hand side where these blue and red lines are, which represent beams of light, you see 2 photon sources. So these are devices which make single photons, so single particles of light. And we make 4 of them, of which, for reasons that are not worth wasting too much time on, we have to sacrifice 1 in order to kind of trigger the experiment. So we are left with 3 photons, and these 3 photons go into a large-scale linear optical device, a photonic processor, as we also call it. And in this processor, they can feel arbitrary long-range hopping interactions. So you can make Hamiltonians where the photons can jump, right? So the photons are confined to channels on the chip, and they can arbitrarily jump between these channels in a way in which we can fully control. And this is quite a special thing, right? So this is kind of the I would say the new piece of technology that enabled this experiment is the large number of optical modes that you have there, the low optical loss, and the high degree of control that you have over your optical modes. And so what we do is we program out some suitably randomly chosen Hamiltonians on this chip, and then we look at the output statistics. So the 4 channels collectively are the global system, and then a single channel, and we choose channel 1 without loss of generality, is the subsystem, right? And so the idea is that you arbitrarily generate these Hamiltonians, you compile them onto the chip, you run them for a certain amount of time, and then you see, as you turn up that time, you see the emergence of thermodynamic behavior. And then the other thing that you can do is you can run them backwards, right? So you see that there are 2 boxes drawn on the chip, a blue box and a yellow box. And what you do there is you generate, so for the first half of the experiment, we just set the yellow box to do nothing. It just lets the photons straight through. It doesn't do anything to them. And we, in kind of the second half of the experiment, what we do is we task the second part of the chip to undo what the first part of the chip has done, right? So we know what the state after the first part of the chip is because we've measured that. And now we see if, having created that state, we can reverse time, right? So this is, in a thermodynamics, in the context of this example that I just said, that you open a hatch between 2 volumes, and all of the gas that is in one of the 2 volumes just fills up the whole space. This is kind of reversing time and watching all of the gas coalesce back into one of the 2 volumes, right? So really doing something that is forbidden by thermodynamics.
Okay.
Go ahead.
One thing I'm struggling a little bit with in this picture is the notion of a closed system. So we have the photons that we now send through this programmable optical chip, I think is the right terminology for it.
Yes.
And this, to me, given that it's programmable, it seems like we're feeding it in some way. But nevertheless, this is what we consider conceptually as being the closed system, or am I thinking about that in the wrong way?
Well, it's closed in the sense that the photons have nowhere to go, right? So, I mean, it's definitely not closed in a kind of informational sense, right? So yes, definitely, this chip talks to the outside world in various ways, but this is precisely how any quantum computer works, for example, right? So if you consider the people who are busy building a quantum computer, then the goal is to have an isolated quantum system with which to do your computations on. But the way in which that system is being driven, right? So the program that is being executed on that system is very much something that is subject to external input, right? And so, you have to think of this more in terms of that nothing is getting out rather than that something is going in, right? So something that would, for example, break this being a closed system is if we would, open up, right? You see this dotted line that is covering the first 4 channels. If we would open up that line and let the photons go out into the lower modes, then we would have converted the closed system into an open system.
Mm-hmm. Okay, understood. And also when you feed this with photons, do you send a number of them at the same time through these entry points, let's say, to the processor, or do you send one photon at a time at one given entry point?
No, we send 3 of them simultaneously, and that's very important because they have to exhibit quantum interference, which they can't do if they are arriving at different times through the chip.
Mm-hmm. Okay, understood. On the architecture, is there anything else that's important to highlight from your perspective before we start looking at the results?
Well, I mean, maybe it is worth mentioning that this chip, right? So I mentioned earlier that I have both an academic side and an industrial side, and it's maybe worth mentioning that this chip was produced by QuiX. So this is a really nice, it's a really nice demonstration, I think, of what you can do. I won't put on my advertising hat too much, but I do think that it's a really nice illustration of the kind of fundamental physics that you can do with these kind of devices.
Mm-hmm. I mean, maybe as a small detour to talk about those topics as well, would you mind just summarizing what the industry applications are of this kind of technology? So we talk now about the physics surrounding it. Would you mind just summarizing what are the applications in general that can be associated with this?
So photonic integration, photonic interference, right? Linear optics represents a near-term model of quantum computation. And like all near-term models, it's still an enormous open problem whether this is still good, whether this is good for anything, right? So in some sense, if you ask me, well, what does the existence of this device mean for quantum computing? I would almost say it's a proof of principle of, the amazingly complicated systems that you can build in photonics, right? So if you consider, for example, the quantum advantage demonstrations that have been done, in Yan-Wei Pan's and Xiaoyang Lu's lab at USDC in China, but also in other places, then those are the largest controlled quantum systems in the world by dimensionality of the Hilbert space, right? And so photonics is just very good at building these highly complex, highly controlled systems. And this is just one example of that.
Okay. And the space then, if I take your point correctly, is that the main area of interest for this is quantum computing, photonic quantum computing at the moment. There are no, let's say other areas where this kind of technology is currently being applied, but
no, there are many.
Okay.
Sorry, there are many other areas, right? So there's these large-scale integrated photonic systems. Like we could do a whole podcast just about those, right? I mean, they are used in optical beamforming. They are used as accelerators for AI, right? They are used to solve integral and differential equations. There's a whole, this is a whole subfield in and of itself to try and encode interesting computations in these devices classically.
Okay, thank you for pointing that out as well. Good, then I think we can move on to the results then. So you have a few measurements that are presented in the paper, and let's switch down to those and we can discuss what they mean. You have 2 subparts of this figure, so A and B, for the 2 different Hamiltonians that you used. Maybe it would be good to quickly discuss the choice of those first. So how come you had a hopping Hamiltonian and then a long-range Hamiltonian? Why these 2 in particular for this experiment?
Well, to put it very bluntly, because those are the classes that we have access to, right? So this is one of these examples of, well, we do the thing that we can do. And particularly the long-range Hamiltonian is one where photonics is very good and where photonics also gives opportunities that many solid-state systems don't have, right? So because the coherence times in photonics are very large, it's very easy to have systems that are very far apart interact with each other. And so it's sort of natural, right? If you know that, it's sort of natural to try and look at systems which exhibit long-range interactions.
Mm-hmm. Okay. And for the hopping Hamiltonian, was that so? Can we maybe talk briefly about what these Hamiltonians represent, if that's possible? Like, what is, conceptually speaking, the difference between the hopping Hamiltonian and the long-range Hamiltonian?
Okay, so the hopping Hamiltonian just assigns, as time goes forward, it assigns some probability amplitude to a particle moving, to a photon moving one side to the left or to the right. Right, so you have these optical modes, and you can think of them as, sites on a lattice, and in every time step, every particle decides whether it's gonna stay where it is, jump to the left, or jump to the right. Mm-hmm. And then in the long-range Hamiltonian, the particle has additional options, so it can move not just one to the left or one to the right, but it can in fact move to any side on the lattice. Mm-hmm. With a probability that is independent of its probability to move to any other side on the lattice.
Okay.
And so the physics there is much richer.
Okay, understood. Cool. So then let's dive into the figure itself. So we have mm-hmm. two parts of the figure here, one part at the top and then one at the bottom. Would you mind describing or explaining what these histograms describe?
Yes. So as you go from left to right, you are increasing the time over which that interaction runs. So you see in the left column, right? So if you read this figure by column, right? Each column represents a different time slice. So the left column is 0.1 units of time, and then the rightmost column is 5 units of time, and the rest is in between. And then as you look at the rows of the figure, the first row represents the output statistics at a subsystem, right? So this is looking at the system thermodynamically, if you want. And so the gray bars are the canonical thermal state. So this is your Boltzmann distribution with some small corrections for the finite size effects, because we cannot simulate a universe that is large enough that we can completely push the finite size effects away, but that's really a detail. So that's the gray bars, and then the dots, the black, blue, and red dots are the theory prediction, the prediction for particles which do not entangle, and the prediction for particles which do entangle, respectively. And so if you look, for example, at time equals 1, and you look at the red particles, right, which are the particles that we care about, you see that by running this interaction forward, you have now in fact generated a state that is very close to the canonical thermal state. Right, so this is kind of proof of the fact that that this mechanism is working, right? And then what is on the other three rows is everything associated to reversing time, right? Mm-hmm. So there are basically 3 experiments. The first one is kind of a check on the first row, where you don't just look at what is happening in a single mode, but you look at what is happening on all of the modes, so on all of the sites. And then the other 2 are, right, so the third one is straight up reversing the interaction, right? So this is, it's like dropping a coffee cup on the table and the coffee goes everywhere, and you kind of wave your hand and it just jumps back into the cup again, right? Mm-hmm. So that's kind of what you're doing there. And then the last one, this is kind of for technical reasons. It turns out that you also have to take a Fourier transform, and this has to do with the fact that these particles because they are non-interacting particles that interact essentially via the symmetry requirement on the wave function because they are bosons. You have to verify the degree to which they are indistinguishable particles. But kind of conceptually, this is not important, I would say. Right. So the main rows are the first one and the third one that you should really care about. And then, so for the hopping Hamiltonian, there is just a single hopping Hamiltonian that you can dial. But for the long range one, you can kind of randomly adjust these coefficients of where the photons can jump to. And you can see, right, so we did this 25 times. So we generated 25 random sets of coefficients and ran those through this procedure. And what you see now is that, for example, if you look at time equals 1, you see that the whole point cloud for the indistinguishable particles, so for the red circles, is clustering around the canonical thermal state. Right? So now you see this effect that it doesn't really matter what kind of interaction you dial, you just dial some interaction and you always get this thermal state out. Right? So that's
follow-up question on that.
Yeah?
So that seems to happen at t equals 1 in this case. Is there a time dependence for, like, depending on, let's say, what kind of Hamiltonian or what kind of parameters of your Hamiltonian you use in this case? Would the time until you reach a state like that depend on those parameters, or is that more or less stable?
Yes. No, so that does depend. So if you go back to the hopping Hamiltonian, actually, you can see that it's even, right, so the physics is even richer than that, right? So what you see there is that at t equals 1, you are very close to the thermal state, but at t equals 5, you're very far away from the thermal state again. And so what has happened here is that you are starting to feel the size of your closed system, right? And so there's a whole theory about recurrences, as we call them, right? So where this system, there's kind of this entanglement that is being generated, and at some point you can think of this as like an information wave that is propagating, and at some point this information wave hits the edges of your universe and kind of reflects back. And so at some point you start to get interference of this wave pattern with itself. And you could kind of compare this with, imagine you take a, one of these perfectly round pools, right? Like these small pools that are meant for toddlers, right? And imagine that you throw a stone precisely in the middle of the pool, right? What you're going to get is you're going to get waves flowing out to the sides of the pool, reflecting back, and you get some water jumping up right in the middle of the pool, right? And so something similar is happening here, right? You inject photons. Those are the stone in this analogy. The information that these photons have gone into the system propagates. It hits the edges of the system. And when that information comes back, interesting things start to happen. And in contrast, the long-range interactions, you see that once you go to the thermal state, you kind of stay there, right? So this is kind of comparable to, instead of taking a perfectly circular pool, instead you go to the garden center and you buy some like nicely, elegantly shaped, kind of natural shaped pool, and you throw a stone into that, right? So now the information also eventually hits the edges of the universe, but because it's much more scrambled, it doesn't all come back at the same time. And it turns out that means that you don't see the effects of it nearly so much, right? So there is a point where you would go away again, but that point is much further down in time than what you can see here, right? So there's a whole there's potentially even quite some interesting follow-up research that you could do here to study, how that information is propagating through that system.
Mm-hmm. Yeah, I would say that's exactly one of the follow-ups I would like to raise with respect to the hopping Hamiltonian. If we have this kind of system where you have something approximating, the distribution you would have for something that follows thermodynamics, and then you have a deviation from that in the second step as well.
Mm-hmm.
If you look at the entanglement between the different particles in here, would you then see, bringing this back to what we talked about before, that
Mm-hmm.
you have information being stored in the entanglement? Would this somehow be, could you think about this analogously to a strong entanglement existing first, that entanglement getting weaker, and then a strong buildup of entanglement again? Or is the strength of the entanglement itself not directly equatable to the information contained in the entanglement?
Well, what you would get is you would get oscillatory behavior, right? So if you would take this system and you would map it out for many time steps, what you would see is that the information would go back and forth between being in the subsystems to being in the entanglement to being in the subsystems to being in the entanglement, and so on and so forth. And the speed of that oscillation is set by essentially the eigenvalue problem of how information propagates through this system, right? So there's, this is a set of coupled harmonic oscillators. You can define, normal modes and so on and so forth. And so if you would, would compute, right, each of these bits of information moves around at a different speed. And so you can think of it as like a bunch of clocks that are all running at different speeds. And when all the clocks strike 12 simultaneously, the information goes back into the subsystems. And what you are doing for the hopping Hamiltonian is you're setting all of these clocks to run at integer multiples of each other, right? Mm-hmm. So the first clock is running one circle every hour. The second clock is running one circle every 2 hours. The third clock is running one circle every 4 hours, and so on, right? And so actually what all the other clocks are doing doesn't matter, right? It's the slowest clock that is going to determine when the information comes back, right?
Yes. Mm-hmm.
Whereas in the long-range system, the spectrum is much more complex and much more random. And so now it's like taking a bunch of clocks and setting each one of them to a random speed, right? And now you have to wait until they have gone kind of the least common multiple of all of these speeds, right? Which if you're very unlucky can be a very, very long time before they're all striking 12 again simultaneously. And so that's why kind of the more random you make the system, right? Again, if we take this analogy of throwing a stone in a pond, right? Then for a very round pond, all of the waves come back to the same spot after a single oscillation. For a very irregularly shaped pond, these waves are going to slosh around, right? And eventually they're all going to like roughly meet each other in the middle again. But you're going to have to wait a very long time before that happens.
Mm-hmm. Understood. Okay, very interesting. We have one more figure in the paper that we haven't yet had time to discuss. We're also rolling up on time, and I'm not sure whether there's anything you think is critical to talk about with respect to this function. If there is, then I'm happy to give you a few extra minutes to talk about this one. Otherwise, we could maybe round up with some conclusions on the work and sort of next steps in terms of research.
Well, I think I can be very brief about this figure. So this figure essentially takes the results from the last 3 rows of the previous figure and condenses them into a number that shows that the system is a closed system, right? So this thing that I've been talking about all the time, that the nice thing about this is that you can reverse the interaction. This is the figure that proves that.
Okay. Would you mind describing very briefly how that happens, or is that too technical? I don't know if then we're getting into perhaps too long of a discussion.
Well, it's so that the technicality of it here is that you have to witness the degree, witness in the technical sense, the degree to which the state that you get out resembles the state that you put in, right? So you want to show this time reversal symmetry. All right, can you actually prove that the thing that comes out looks like the thing that you put in? And the number that's on the y-axis here is the extent to which these two things are provably similar.
Okay, understood. But then let's leave it at that for the figures. Just in terms of next steps for research in general, applications that are related to this, is there anything you would like to conclude with when it comes to this paper, the impact it might have, or anything of the sort?
Well, I think first of all, this is the first time that anyone has thought to use photonics as a system for studying the interrelations between quantum mechanics and thermodynamics. And I think that that's a very powerful idea. And so follow-up work that we're trying to do is very definitely about how far can you stretch that analogy, right? And when do you get to the point, right? Is there a point where you, for example, actually start seeing things in photonics that have been predicted in thermodynamics, but that for whatever practical reason you cannot access in other material systems, right? So building out that analogy, I think, is a very interesting line of work. And then I think the other much more technical side of things is that you can also think of this as like a very rudimentary form of quantum simulation, right? Of analog quantum simulation. Because what we're trying to do is we're trying to see some physical effect, and instead of trying to study it in nature, we build a system where we can actually program out that effect controllably, and then we run it and we see what happens, right? So in that sense, I think that also shows the promise of photonics for that kind of research.
Yeah, I agree. Good. But with that then, Jelmer, I would say we can round up the interview here. Thank you very much for explaining these concepts to me. I certainly learned a lot today, so thanks a lot for that.